Hello, and welcome to this video discussing how to interpret the output of your EEG classifiers. So in this little video, what I'm going to be talking about is three different stages when it comes to discussing output. First, we have deciding what metric to use as our classifier output. We'll then move on to what kind of statistical test you'll use to see if the classifier generalizes across subjects. And then lastly, we'll discuss how to control for multiple comparisons here. So first, we'll get into talking about choosing your classifier output. So we'll start off with what is the simplest approach to assessing classifier performance, and that's accuracy. Accuracy involves comparing the label assigned to a given child by the classifier, so that's the predicted label, with the actual label. If they match, then the trial gets a 1. If they don't match, then the trial value gets a 0. And if we can look on the right, we have this little graph which tells us how our classifier is doing. We've got the dotted line, which is the hyperplane. We've got the yellow dots, which refer to one category. We've got blue dots, which refer to the other category. So these are the true outcomes. These are what we know. And now we want to see how the classifier predicts the labels of each one. So given the hyperplanes here, it's going to predict that anything above the hyperplane, so these 5 guys here, are going to belong to the yellow category. And anything below the hyperplane here is going to be belonging to the blue category. So as we can see in the case, this is not the, well, as we see in the plot, this is not the case. So we're going to have to consider how many trials are correct and how many trials are incorrect. So if we look at this, we've got 1, 2, 3, 4 of the yellow stimuli which are correct, 1, 2, 3, 4 of the blue stimuli which are correct, and 2 which are incorrect. So altogether, that's 8 trials which are correct out of 10, which gives us an accuracy value of 80% or 0.8. And it's as simple as that. It's just literally counting up how many times it's correct and comparing that to a number of trials. So this is obviously a really handy method, and it's really intuitive. Everyone kind of understands that the classifier is right 80% of the time. It's really easy to understand. However, there's definitely some drawbacks from this simplicity. And perhaps the biggest problem is that the results across participants are unlikely to be normally distributed. In the example above, we have 10 trials, so the classifier performance can only take 11 unique values. And what I mean by that is that there's only 11 unique outcomes of correct, incorrect in this data. So there's 0% classifier accuracy where none of these trials are correct. There's 10% accuracy where only a single trial is correct. There's 20% accuracy where there's 2 trials correct, and so on and so forth, all the way to 100% where all 10 trials are correct. But because there's this sort of ordinal limited range of outcomes, when we look at group performance, it's really unlikely to be normally distributed, and that can have quite serious implications on what statistical tests we can do later on. We'll probably have to rely on non-parametric tests, which do have their own limitations. So yes, that's accuracy, really intuitive to understand, but also because of its simplicity, it has a few drawbacks. I'll next talk about decision values. So a decision value, also known as a d-value, tells us how confident we are about our classification accuracy. So we're no longer doing this binary, yes, it's correct, no, it's not correct. We're doing this, how confident are we that it fits the right category? So yes, the decision value is a continuous measure of the classifier, which in case of LDA and similar linear classifiers tells us the distance from a particular sample. Let's take this guy, and tells us how far away it is from the decision boundary. So it's quite close, so we're not particularly confident about classifying this stimulus as a blue stimulus. But if we look at this guy down here, it's much further away, so the d-value is bigger because there's greater distance between that item and the d-value, and we can say we're more confident. And we can also just do that for all of them. and we get these nice little dotted lines. And then we can say the further the stimulus away is from the dotted line, the more confident we feel it belongs to the category on that side of the stimulus, that side of the hyperplane. So in this case, the yellow dot here, though it's misclassified, it's saying it's relatively confident it's a blue stimulus. But this is quite nice because it gives us not a single value, it just gives us a continuous measure of how confident we are about classification accuracy. So these D values can range from 0, which means that they sit directly on the hyperplane. So any dot which sits right there has a value of 0. And then it can range from upwards of plus infinity, miles off this direction, or negative infinity, right off that direction. So because of this, we don't really need to worry about such boundaries or nominal scales, binary scales, limiting or distorting the underlying distribution across a group, meaning that parametric statistics are back on the table for later analysis. However, these D values are, or it's say, unitless. So they don't actually carry a lot of information in and of themselves. So a D value here of 5 is kind of difficult to interpret. We can say that a huge D value relative to a small D value has meaning. We can say that because this D value is larger than this D value, we are more confident. But we can't definitively say that we are absolutely sure that this one's, we're very confident that this blue stimulus belongs to this category, because that's just not what the D value statistic is telling us. So in short, the D values are this nice little way to say how confident we are. They're a continuous measure, so they're great for use in parametric statistics, but the actual D value itself, that unit, that number you give the D value, doesn't have any meaning. We can't say how confident we are based on that D value alone. We can only say how confident we are relative to another stimulus. So we'll move on to the alternative, which is a combination of accuracy and D values, and this is probability. This still sits in the range of telling us how confident we are that our classification output is correct. So again, we look at the distance from the hyperplane to the stimulus, but we scale it between 0 and 1. And this tells us the probability that our stimulus category, which we predicted, matches the stimulus category which actually belongs to that trial. So if we are 100, if a probability is close to 100%, then we can say we are really, really certain that it belongs to the correct category, or it belongs to this category. Whereas if it's really close to 0%, then we can say we don't really have much clue at all, or it really belongs to the other category. So like D values, it's a measure which tells us how confident we are about a predicted category. So it can really help us get a feeling for what, how different trials interact and all of this. But unlike D values, it has like a meaningful measure almost. The fact that if we say we've got a probability value of 0.7 means that we can say that, hey, we're 70% correct, we're right, sorry, we're 70% sure we're right here, which is a little bit more easy to interpret, a little bit more easy to understand than most D values, which is quite handy when you're just looking at classifier output and really want to say how impactful, how useful this classifier is at separating boundaries. However, once again, this does have the issue where the output variable is bound between the values of 0 and 1. And while it's not as severe as accuracy, where the decision was a binary value, the fact that it still has this limit, this 0 and 1 as a limit, means that it can introduce issues with the normality of the distribution again. And this means we once again need to be careful about what kind of statistics we apply to the later analyses. So we can now just have a quick think about which metric and the pros and the cons of each metric. So we've got accuracy, and it's really easy to understand. It really tells us just how well our classifier does, how many times is it right in a percentage, which is really easy to compute and it's really easy to understand. However, because it's a binary value, because it just gives us a value between 0 and 1 on a single trial, then it's unlikely, or at least the underlying distribution is not going to be normal, and this is going to impact what kind of statistical tests we can do on our data. And we can overcome this issue by moving on to using either decision values, that's d-values, or probability, both of which are continuous measures of confidence of our classifier. They tell us how far away a particular stimulus sits from the hyperplane, which is great for us to be able to use parametric statistics, which usually have a bit more statistical power. But in the case of d-values, these are often arbitrary values. So if we have a d-value of 5, that has very little meaning. It could mean that our classification is working incredibly well, but it's always getting great, it's always super confident. But it could also mean that the classifier is just like, well, maybe it's just this category, but it could also be the other. We're not confident at all. The arbitrariness, the uniqueness of decision values makes it a little bit difficult to interpret how confident we are in the classifier. Probability addresses this by essentially bounding the decision values between 0 and 1 and turning it into a percentage. With obviously the closer we get to 100%, the more and more confident we are in our classifier, which again is very easy to understand. If we say our classifier is correct 100% of the time, we know we're doing great. However, because we are once again bounding the bounding the outcome between the 0 and 1, then it does mean the normality is likely to be compromised, and therefore the use of parametric statistics should be something to be careful about. So now, having just given a couple of hints about parametric and non-parametric statistics, I'm just going to give you a little bit of a brief overview of what statistical tests you can use to quantify how well your classifier works in a sample and how that would generalize the population. So yes, we have our measure of a classifier performance, and now we want to know whether the performance of this classifier is important, whether it's meaningful. Now, the typical approach is to use some sort of inferential statistical test to see whether the performance of a classifier differs from chance or differs between conditions or whatever baseline you like to use. Now, these inferential tests fall into two families. They are either parametric or non-parametric. And the principal difference between these two types of tests is that the parametric tests make assumptions about or make a lot more assumptions about the underlying data. Most often, this assumption is the data is normally distributed. In contrast, non-parametric tests make no assumptions about the data or the distribution, or very little. So in practical terms, this distinction means that parametric tests usually have much more statistical power than non-parametric tests, which is great if you really want to tease out a small effect. But the non-parametric tests are much more robust when the distributions are not normal. So it's always important to consider these differences and how they relate to your chosen metric of classified performance. I say this because a number of those metrics we've chosen will violate assumptions of the parametric tests, these sort of normally distributed tests. This problem is perhaps most clear for measures such as raw accuracy. So this is whether this binary decision, are we correct, are we incorrect? Because of this really clear binary outcome, no participant is ever going to show you more than 100%, or it's never going to show you anything less than 0%. And these boundaries often damage the distribution of the data, so it's not so normally distributed anymore, and therefore can violate some of the assumptions of practical tests, parametric tests. So if you wish to use measures such as classifier accuracy, it would be safest to use non-parametric tests for inferential tests. If you really want to be certain about distribution of your data, you can also run tests for normalities such as the Kolmogorov-Smirnov test. I'm not going to dive more into that topic today. Okay, so we've decided on the test. We've decided, do we want to use a parametric test? Do we want to use a non-parametric test? Well, great. We now need to decide what's going to be our null hypothesis. What are we going to be testing against? And usually our null hypothesis is it doesn't differ from two conditions, they don't differ from one another. whether that's 2 different experimental conditions or whether that's 1 experimental condition differing from chance. This is up to you to decide, but right now I'm just going to really in particular talk about those circumstances where you're evaluating your classifier relative to chance. So yes, we've decided that we want to test, but how are we going to do this? Well, there's 3 common approaches, and as always, I'm going to start off with the easiest. So first, we can say that the chance performance in a binary classifier, so we've got 2 categories, it's going to be 1 category or the other category. We can say that that chance performance is 50%. So this is our null hypothesis that, the null hypothesis in this case would be that the observed classifier performance does not differ from chance performance, which is 50%. Now, this is assuming we're using probability or accuracy, but if we were to use d-values, then we would say chance performance is 0. So that's where just the d-values sit on the hyperplane. Now, this approach has the benefit of being really simple because it's just a 1 sample t-test in this case, but it does have a few assumptions, but the actual chance performance is 50%. And though it seems to be a very sensible assumption to make, there's always times when perhaps there's overfitting, perhaps there's bias in the training or test data, but chance performance doesn't actually sit at 50%. Maybe there's just some weird bias, which means that the chance performance actually sits at around 49%. And then when you're testing your observed data compared to your real data, then you still get this effect sitting there because there's just minor differences in what we assume a null hypothesis to be, which is 50%, and these biases present in the data. So it's usually not wise to assume your classifier performance is straight at 50%. It's better to find somewhere to benchmark it based on other parts of the data. So this is where the second approach comes in. So in the second approach, we might say that chance performance is pretty much decoding before the stimulus is shown. Or during any other control period, like eyes closed or something like that. So when the participant is not engaging with the stimulus of either category, then we can see how the classifier applies to that data and then use that as our baseline. So we would say that our experimental condition, the classifier performance, is no better than what happens pre-stimulus. So this is a little bit better because then if there's biases in the data, then it's applied to the experimental data, but it's also applied to the pre-stimulus data. And so that essentially takes out the bias, assuming the chance performance is at 50%. However, in some experiments, participants may be able to predict what stimulus is coming up. If you've got some sort of sequence learning paradigm, which has got a predictable sequence, then they might know before the stimulus is shown what category that stimulus might belong to. Therefore, there will be this sort of evidence accumulation arising just before the onset of the stimulus, and therefore you will see some decoding performance happening before the stimulus onset. And this is going to obviously be a problem because then this is not chance performance anymore. This is actual performance of predicting what's coming up. So if you're going to compare your main effect to a pre-stimulus baseline, it's best to make sure that it's really not, this pre-stimulus baseline really has no interference from other stimulus categories. And then lastly, we can generate our null hypothesis by just randomly shuffling the labels. And personally, this is one I would advocate for. In this situation, what we would do would be we first apply the classifier to our test data, and we see how the predicted labels match up with the observed or the true labels. We get our accuracy measure, and then we randomly shuffle the labels again of the we randomly shuffle the true labels, so we get a permuted label, and we calculate classified accuracy once again. And we can keep doing this and keep doing this until we get this nice little distribution of what accuracy would be under the null hypothesis under just random labels. And then we can take this mean of this accuracy across all these random permutations and get a single nice little value which tells us what would we expect to see based on chance. And this is a much more robust way, perhaps the most robust way, to make sure that you're comparing your observed performance to chance performance of the classifier. But of course, this also has the limitation of randomly rerun or randomly resampling and permuting. It just takes longer. It makes way less assumptions from previous methods. It's not assuming the baseline is 50%. It's not assuming pre-stimulus window is a good representation of the data. It's just purely randomly randomly shuffling the data till it finds a nice distribution of what chance performance is, but it just takes longer. So again, it's up to you which approach you would decide upon. The shuffled approach does take the longest, but it's not that difficult if you just shuffle for labels. It doesn't take too much longer. But then pre-stimulus performance window is also quite a nice way to do it. But I would say that the idea of just assuming the baseline is 50% is a risky assumption which should be avoided. Okay, so then this last little section, I'm going to be talking about multiple comparisons and how we compare or control them rather. So multiple comparisons, whenever we run a statistical test, I'm sure you've heard about this all before, we return the p-value of that said test. And as a working definition, this p-value is the probability of the observed or more extreme difference if a null hypothesis is true. In psychology and neuroscience, this alpha threshold of 0.05 is most common, and any p-value that falls below that threshold is deemed to be significant. So if you run your statistical test and your p-value is below 0.05, and you say, yay, we've got this awesome result, let's write it up, let's publish it. Because we've decided that in cases where the null hypothesis is true, 1 in 20 chance of the observed or more extreme effect is due to chances and acceptable risk. I mean, it's worth noting that this threshold is totally open to debate, and there's obvious limitations to it, but we're not going to get into that today. But this also doesn't hold up if we start running a second test. If we run a second test, the probability of interpreting one of these as a null effect as something significant has increased. And the more and more tests we run, the more and more likely it becomes that we're going to find a positive result, which is simply down to chance. So if you keep on adding tests, you're more and more likely to find a completely nonsense significant effect. So the art of multiple comparison correction is really addressing this problem. So there's 3 methods to do it, and I'm going to kick off with the Bonferroni correction, which is perhaps the simplest, and it's definitely the most conservative approach you can take. And all you need to do for this is you take your original alpha threshold, so this is alpha, which would be 0.05, and you simply multiply it by the number of tests you're running. So if you've chosen your traditional alpha threshold as 0.05, then if you run two tests, you would say 0.05 times the number of tests times 2. That becomes 0.025. So then if we have a significant effect, it must be below 0.025 as opposed to 0.05 if we're running 2 tests. If we were to run 10 tests, then this threshold would drop to 0.005. And therefore, any p-value would be below 0.005 for it to be considered significant. Now, it's really that simple, which is maybe why it's appealing, but it's worth considering that this is an incredibly conservative approach, and it assumes that every statistical test you're running is independent of every other test you've run there. And when you're doing time series analyses, when you're doing EEG analyses, usually that's just not the case. In most time series analyses, there's going to be some smoothing or some smoothing that's been applied, which means that the data at time point 1 is to some extent loaded at time point 2 and the data at time point 3, and so on and so forth. Therefore, to treat the statistical test at each time point as independent from every other neighboring time point is, I'd argue, too conservative, and you're really going to increase the risk that you get a false negative. So that's when you assume there's no effect when in fact there is. Correction. Now this is a slightly less conservative approach that aims to control the number of false positives, but also control the number of false negatives incurred in the analyses. And this is done by making a few concessions that, yes, there'll be false positives in the data. We're not going to completely obliterate those chances like the Bonferroni approach does, but it also gives you that little more statistical power and also reduces the chance of discarding an interesting effect and misclassifying it as a false negative. So how's this done? It's very much like the Bonferroni procedure if it were done in a sequential manner. So you first take all your p-values from your time series. So let's say we analyzed 8 points in time and we've got 8 p-values. We first organize it from highest p-value to lowest p-value. And what we're going to do is we're going to step through each p-value and then apply a sequential Bonferroni procedure to it, essentially. So for the first p-value, this is the first test we've looked at, so the threshold is 0.05, your bog standard alpha. Because the p-value is not less than the threshold, then we wouldn't consider it significant. We do this again for the second p-value. So this is the second p-value we're considering. So Bonferroni correct that threshold and we get 0.025. And again, it's not significant. So a third time, so this would be significant if we weren't controlling for multiple comparisons because it sits below 0.05. But if we look at the Bonferroni corrected p-value or the sequential corrected p-value, which is now 0.017, then it's still not significant. Now we go for the fourth time, and look, we've got a lovely effect. Well, it's still a little bit very close to a boundary, but it's significant, we would say. But this p-value now sits below this sequential threshold, so we say it's significant. Now, the important thing to remember is that once we've found this threshold where the data starts to be significant, then this sits as the threshold. But this is now our alpha threshold. Anything below 0.013 is significant. Even if we look at more tests, the threshold sticks at 0.013. So we can look at the next p-value and we'll still use this same threshold of 0.013 and it's significant. Same threshold again, same threshold again, same threshold again. So as you can probably get an intuition, this is a lot less conservative than the Bonferroni. That's which is really nice about it. It's much less likely that you're going to get a false negative in your data, but obviously if there's less chance of a false negative, there's also a greater chance of a false positive. So this is just something to remember when using this method. And then the last one I'm going to talk about is cluster-based permutation testing. And this is the, I would say it's a very well-known statistical method in EEG and MEG. And it's really well developed specifically for this purpose, for high-density EEG and MEG. Now, cluster-based permutation testing doesn't rule out statistical tests on individual channels or time points like Bonferroni or FDR does, but rather the cluster-based permutation builds clusters within the data, finds one cluster, and then just runs a single statistical test on that one cluster. So by only running one test, you don't need to correct for multiple comparisons anymore because you've only run one statistical test. So I'm just going to give you a quick overview of how it does it. It first, to find these clusters, to build these clusters, it first takes the difference between two conditions of interest. So perhaps our observed decoding compared to the decoding expected by chance, or maybe it's decoding for remembered stimuli versus decoding for forgotten stimuli, using some metric, often t-values. So then these t-values, which are describing the difference between the two conditions at each time point, each channel, are thresholded based on some value you can define yourself. And any value larger than that threshold is selected. The algorithm then sets out and searches these high-value t-values to find whether clusters have been formed. So it looks for neighboring channels which are also above the threshold and builds these together into clusters. So if there's 3 time points which are all next to each other, all above the threshold, then these are put together into one cluster. And the t-value within this cluster is summed together. And we can say the cluster with the largest sum t-value is the cluster we're going to run our analysis on. So we've managed to reduce a multi-channel time series down into a single cluster, eliminating the need for any sort of multiple comparison, which is great. However, because we've been selecting channels and time points based on the largest difference between conditions, then we've introduced circularity into our analyses. So in other words, we've decided what parts of the data are best to test the analyses on itself. So we need to address this somehow. We need to get rid of this circularity, or we need to add in an unbiased control condition. So we can do this using permutations. So to do these permutations, we randomly shuffle the data between the 2 conditions, and then we redraw the difference between these 2 chance or permuted conditions. We find out those t-values which sit above the threshold. We build these clusters, we find the biggest cluster, and then we now can compare this single cluster to the observed true cluster we have before we shuffle the data. And if we do this 100 times, 1,000 times, then we get a nice little distribution of chance clusters. And we can compare our observed cluster to these chance clusters. So to get our p-value in this case, we can just use a simple permutation test. And we divide the number of chance clusters, which have a value greater than the observed cluster, by the total number of chance clusters examined. So for example, if we generate 100 chance clusters, so that's 100 permutations, and 2 of these clusters are greater than the true real observed cluster, then the p-value is 2 divided by 100, or p equals 0.02. So, and because this has been done on a single cluster, we don't need to do any multiple comparisons. So this is the really powerful method. It's one of the best ways maybe to address the multiple comparison problem in MEG and EEG, because it really takes into account the fact that data at neighboring time points, data at neighboring channels is correlated. And as you can see on the right, the plot over here, you can see that the cluster-based approach outperforms the Bonferroni correction. It kind of really pulls out those extra few points, but it also doesn't come up with all these like little spurious effects. However, there's always drawbacks, and the main one to remember is that just because you form a big cluster at a particular time point or at a particular channel, it does not mean that the significant difference between the observed condition and your baseline is significant at this time point. So we see this grey box here, we see the effect is at around 500 milliseconds, but the nature of these clusters and how we run these tests mean we cannot say the effect is significant at 500 milliseconds. It's a bit of a deep dive maybe to get into, but if you're interested, you can read a bit more here in Maris and Ostenveld's paper. Okay, so a quick comparison of the multiple comparison methods. So I've discussed 3 methods for correcting these multiple comparisons, where you can say 4 if you consider doing nothing an option, but I would say do not consider doing nothing an option. And in the grand scheme of things, you need to pick a method which is best suited for what you consider to be most important when you're analyzing your data. If you want to be absolutely certain that there's no false positives in data, then Bonferroni at the far end here is the most effective method. It really reduces the chance of you finding any false positives in your data, but it comes at the cost of increasing the false negative rate. But then, yeah, maybe this is just too strict for you, and there you can kind of consider maybe the false discovery rate we've got down here. I mean, they're pretty much comparable here. But unfortunately, one thing to consider about the FDR, which though it's less, there's less chance of a false negative, it does mean there's more chance of a false positive. It also doesn't necessarily wrap your data into a neat little package. You're not going to get one single significant effect. You're going to get lots of little blobs. You're going to have samples. You're going to have brief 20 millisecond effects, which is kind of difficult to interpret. And then you could always just jump onto the cluster-based permutation tests here. And these cluster-based permutation tests only bring out a single cluster, only test once, so you have a single effect you can report in your analyses, which really helps with the interpretation. Of course, it also has its own limitation in that it says that because of how it builds these clusters, how it contrasts these clusters, it means you cannot say where or when the effect occurred, but only simply that it did. So there's no silver bullet for addressing multiple comparisons. You just need to really think hard about which method best suits your experiment and then push forward with that. Okay, so thanks very much for tuning into this one. Again, this is just a bit of more further reading I'd recommend. So you've got one by Linquist here, which is a really nice one to just discuss the nature of multiple comparisons and the different approaches you can take. It talks quite a bit about Bulgaroni and FGR methods. You can also look at Murray St. Austenfeld's paper for more information about cluster-based permutation tests. And then going back to the earlier part of this talk when we were looking at classifier outputs, accuracy, d-values, probability, then you can also just turn to Matthias Trader's paper on MVPA-LACE. So some nice little bits of reading there if you're a little bit more interested in the topic. But for now, thanks for tuning in, and I'll speak to you soon.